Hello guys, welcome again to this series which is on machine learning fundamentals. Uh, in this particular episode, which is episode 16, and we are in the third part of it. Second part, we had discussed, in fact, various concepts that were related to, different unsupervised learning, machine learning algorithms. And in that category, we had discussed, in fact, certain things like, for example, linkage. And in fact, we were discussing about the linkage. I had, in fact, in the previous part of this particular episode, which is 16, I had just told you that what is single linkage, complete linkage, average linkage, and word linkage. Actually, we had discussed single linkage and word linkage in quite a detail, and then these complete linkage and average linkage as well. I had shown you one uh, animation which was in fact giving a graphical visualization of this. And I shall be starting from the same point again, and I'll give you, the proper definition which I had, in fact, told you. And then from there, we'll be moving forward with DBSCAN, which is an unsupervised type, and will be, in fact, in a very detailed manner, we'll be just discussing about that and implementing DBSCAN in Python. So let us just start. I'll put my presentation. So this is exactly the point we left in the last part we were discussing about. This was, in fact, the figure which I showcased to you, final clustering comparison across linkage criteria when we run that program. So this was the figure which was there. And it is showing this single, complete, average, and word linkage. And now a little bit of a definition of these, which I had, in fact, promised last previous part of this. In the single linkage, what happens is you will notice that long chain like clusters that we can see here as well. These are the long chain like clusters which are there. Points connected through nearest neighbors, so we can see that points are connected through nearest neighbors here. It is sensitive to noise, creates stretched clusters. We can just see that, if you see the first figure itself on the left hand side, these are stretched clusters. So it is sensitive to noise. This can cause noise because these are stretched. And there is only one single point which is connecting a cluster with, in a cluster. So you will notice in complete linkage, it is different. You will notice more compact clusters, clear separation. Interpretation is that focus on maximum distance. Tighter groups are there, so we can just see that from the complete clustering. If you just see a same example, you can just see they are much more compact. These points which are there. So you can just say this is a complete linkage. And then we are having average linkage, balanced grouping, moderate compactness. Interpretation is that compromise between single and complete. So you can just see this compromise between single and complete out here. So this is average. And then there is a word linkage. In fact, we had given a detailed discussion we had on word linkage and single linkage. Very compact circular clusters, clean separation. Interpretation minimizes variance, best for structured data. So we know that what is the logic of how the word linkage takes place. So referring to that, if you can just see, this is looking much more compact. So definitely it will be going for the merger only when the variance which we have discussed in the previous part in a quite a detail. Word linkage is much better. It is a best for structured data, and it minimizes variance because we are checking that the resulting cluster which is there, that should be resulting in lesser variance. So if that happens, then only it will be going for merger, otherwise no. So this was a little bit brief about the previous one which we had discussed already, and now actually for this particular part of this episode 16, our topic of discussion is going to be DBSCAN clustering, density based spatial clustering. So this clustering is based on density. You will understand it, and we are discovering clusters through density. So that's what DBSCAN is actually. So we discover clusters through density. How? We are going to, in fact, understand that. So what is the formal definition as far as this density-based scan clustering is, spatial clustering is concerned? So if you just see density-based spatial clustering, what does this mean? DBSCAN stands for density-based spatial clustering of applications with noise. So where you are having the noise, it is an unsupervised learning clustering algorithm. So this DBSCAN is an unsupervised learning clustering algorithm that we already know, that groups data points based on density. So it is grouping points based on density. So if we have to explain this thing in a very simple way, DBSCAN forms clusters where many points are close together. So DBSCAN will be forming clusters where many points are together, and it marks isolated points as noise or outliers. So other points which are there, which are not falling in that particular space, it will be marking them directly as outliers or noise. So simple as that. If we just see k-means, k-means was little different. Unlike k-means, DBSCAN does not require you to decide the number of clusters in advance. It does not ask you the number of clusters in advance. It identifies 3 point types: core points, it is dense neighborhood centers, border points, near cores but less dense, and noise points, outliers not belonging to any cluster. So 3 different points or categories of these points on the basis of which it is creating, in fact, these clusters. So these are core points. Dense neighborhood centers are called core points. Border points are those which are near cores but less dense. And those points which are very scattered kind of thing, those are outliers or the noise points. So they are outliers not belonging to any cluster. Example is, imagine students. So we can just say imagining the same examples of students, but it's in a different way. So we are imagining that the students are standing in a playground. Some students are standing close together in groups, some are standing close, a few students are standing alone far away. DBSCAN will say closed groups of students, they are clusters. Students standing alone, those are noise or outliers. So it's a very basic, very simple example that we have taken here. So it groups by density, not by centriods. So that is something very different in this. And what is the core intuition behind DBSCAN? In fact, core intuition behind DBSCAN is, there are 3 things. One is called as a core points. One is called as border points. One is called as a noise. How density defines clusters. DBSCAN identifies dense regions as clusters. We are coming back to these core points, border points, and I'm going to give you explanation of this. In fact, it's in the next slide. DBSCAN identifies dense regions as clusters while marking sparse isolated points as noise, enabling detection of arbitrarily shaped clusters and outliers. So it is actually enabling this detection because it is taking dense groups as clusters, while as those which are not matching any of these, those are taken as outliers, or those are taken as noise. If you just see this DBSCAN, main terms which are there, first of all, epsilon is there, which is denoted by this letter. This is the radius around a point. So what is epsilon? This is the radius around the point. It answers what it can answer. This is the radius around a point. It answers how close should point to be considered neighbors. So this epsilon, the value of this E, will be designating that how close a point should be to other points, so that it can be called as or considered as a neighbor. So minimum points, minimum samples, this is the minimum number of points required to form a dense group. So minimum number of points that we require to form a dense group, or minimum samples which are there. It answers how many nearby points are needed to call this region as a cluster. So how many points minimum should be there so that we can call it as a cluster, even if they are close to each other. So whether we can, if there has to be some minimum value of these points or samples, which can be called as a cluster. So these are very important terms: epsilon, min points, min samples, and then what min points and min samples actually are for. What is the reason for them? So epsilon and min points, min samples, which are there. DBSCAN parameters, in fact, min samples parameter, min sample, the minimum number of data points required with the E radius to form a dense region and qualify as a core point. So how many of these? Epsilon defines the neighborhood radius around each point for density. We have explained it already. And now these we'll be just giving an explanation of which in fact was discussed there: core point, border point, and noise points. What is a core point? So these are very important things for DBSCAN. On the basis of this, actually, the logic works, and then you will be able to understand the program very well. A point is a core point if it has at least min samples, samples points within its epsilon radius. So core point is one which is having minimum, those minimum number of samples that are there, that are required, and they are falling within the radius of epsilon. Epsilon will be in fact given. If, for example, EPS epsilon is 2 and the minimum samples of 4, a point must have at least 4 nearby points within the radius of 2 to become a core point. So how it becomes a core point? If it is fulfilling this condition, first of all, it should be within the radius of 2, and second thing, the samples that are there should be 4, and 4 points within this radius 2, then it becomes a core point. What is a border point? A border point is not dense enough by itself, but it is close to the core point. So border point is not dense in itself, but it is close to core point. And noise point or the outlier is the one. The noise point is a far from dense region and does not belong to any cluster. It is far from the dense region and it does not belong to any cluster. That is what a DB, this noise point is. How DBSCAN works? Pick a point, check how many points are near it within the epsilon distance. So this epsilon distance is actually given to the DBSCAN algorithm. So in the program also we'll be feeding the value of this epsilon, and we will be checking that within this particular range, how many points are there. If enough points are nearby from a cluster, so if sufficient points are there from the cluster, expand the cluster by finding nearby connected points. So it will be expanding the cluster by finding nearby connected points, and points that do not belong to any dense region are marked as noise. And some other points which are not which cannot be a part, they are far away, they will be marked as noise, definitely, and they don't belong to any of the clusters. They are outliers or noise. So this is a comparison between k-means and this DBSCAN number of needs number of clusters. Yes, k-means needs, DBSCAN does not need. Handles outliers poorly, very well handled by DBSCAN. Cluster shape is mostly circular, but DBSCAN has got irregular shapes as far as the cluster is concerned. Based on, so k-means is based on centrioids. Centrioids, we in fact centrioids, we had discussed this concept in quite a detail when we were discussing k-means. And DBSCAN, definitely it's based on density. We have seen that. Good for noisy data, not ideal, ideal for k-means to be. So k-means is not an ideal algorithm for noisy data, but DBSCAN is very much ideal for the noisy data, because its job is to actually identify the outliers. So this is a simple visual understanding of DBSCAN. If many points are packed together, they belong to same cluster. So they are these you can just see here these black these are the clusters. In fact, here this is a cluster, this is a cluster, and these can be outliers or a noise which is there. If a point is alone, it is probably a noise. So it is a noise. So this is a noise, this is a noise. So these are all noise. So these visual understanding, and where DBSCAN is useful. DBSCAN is used in numerous applications. fraud detection, intrusion detection, medical data analysis, IoT abnormal behavior, customer segmentation, and then GPS location clustering, network traffic analysis, anomaly detection, social media pattern, image segmentation, so social media pattern detection. All of these are the application areas. And one example that can be given in cybersecurity, DBSCAN can detect unusual network traffic. So it can be used to detect the unusual network traffic points that do not belong to normal traffic clusters. So we can just say which are the outliers there, so that we can just identify that traffic. If you just see the Python implementation, this is shown in 5 steps. What happens first is we are importing the library. Second one, we are creating the data set that we can import as well. Here you need to understand that it is giving how many samples are there. We are creating the data, and the noise we are putting 0.08, random state is 42, that we know what it is doing. This creates a curved data set. DBSCAN is good for this because clusters are not simple circular shapes. So it is creating this curved data set. And then step 3 is scale the data scaler. The data scaler is called standard scaler and x scale. So we are just doing this third this one step. Scaling is important because DBSCAN uses distance. And then step 4 is applying this DBSCAN. We are putting epsilon here as 0.3 and minimum samples is equal to 5. So five samples or points should be there within the range of within this range 0.3, which is the radius. And if those 5 points are there, we can just say we are having the main point which is there. The labels is equal to db scan.fit predict x scaled. So here epsilon 0.3 means neighborhood radius that we have already given. Minimum samples is equal to 5 means at least 5 nearby points are needed to form a dense region. So they should be separated by the distance of epsilon 0.3, sorry. Step 5 is display cluster labels, labels print, cluster labels, print labels. So these are being printed. And definitely we can just see that these 5 steps which are there, this we can have an implementation. And I'm having in fact one implementation of this DBSCAN where this exact 5 steps are there. We are having import as I explained, and then we are creating the sample data set. So this is the sample data set we are creating, and then we are in fact scale the data, and then creating DBSCAN model. So this is where we are creating, we are giving this epsilon how much it should be, and how many values samples are there, 5 samples within that minimum. So fit model and predict the cluster. So this is what we are fitting the model. Then we are printing the cluster labels, and then in fact count clusters, how many clusters are there, and print the number of clusters and number of noise points which are there. And then this is plotting a graph which we have done multiple times, 8x6 graph. It is putting x scaled and then labels. And then DBSCAN, it's putting this as a title, feature 1, feature 2, 2 sides, and then the grid. It will be showing, and then it will plot this graph to show. So that this graph exactly will be displayed now. You can just see, I will run this, and you can just see, first of all, it will be giving us the data which is there, I believe. And then afterwards, so this is the data cluster labels which are there. A number of clusters that are formed are 2. Number of noise points, it has detected 0. So I can just show you the graphical presentation of this. So this is something which that has been so these are 2. You can just see DBSCAN clustering. So these 2 are there. There's no noise in this one, and this has been executed. This is one simple example of DBSCAN, and we shall be in fact continuing on this one. And then this is particularly in fact the Python implementation of DBSCAN. These related things we have seen, what they are, and this is in fact giving, you just see this implementation which is there. It is giving us first of all putting the data, and then it is showing that it is having number of clusters that were detected and number of the noise points. Noise points are those which are not falling in that, as we discussed already. So this was the implementation, simple implementation of DBSCAN. I hope that this particular uh, yeah. So this is the very simple implementation of this one. This would have given you a lot of benefit. Shall I hope that you would have got a lot of benefit with this. At least in understanding what DBSCAN is, there are related concepts that we have discussed. In fact, different things, and it is very important for understanding comprehensively what these algorithms which are there, what how they are functioning, and how they are getting us the results. So that is, if we are doing in this particular way, understanding first of all the terms which are there. So you had in fact gone through this. There are various kinds of things which are applications, in fact, and then if you just see, we have gone through various terms as well. So intuition behind this one, so easy. First of all, what density based special clustering is, so I'll wrap it up with this. And then example which was there, and then what is the intuition behind this DBSCAN, how density defines clusters. So then we have discussed the main terms. Epsilon is there, minimum points or and minimum samples are there, min points, min samples which are there. So that is one more thing. And then it is in fact discussing these core point, border point, noise point, and outliers, and the meaning of these, and how DBSCAN works. That is also explained, and the comparison with k-means, and then simple visualization, understanding, and different areas and application areas in which DBSCAN can be used. And then definitely this was the implementation. It's having five steps. We have done it with similar five steps, but we have just put one more thing for just printing the giving a visual output, so visualizing it in an effective manner, and that we have done with that. So I hope that this would have been in fact very beneficial to you, and please provide us your valuable feedback, and your feedback is going to be very critical for us in enhancing whatever services we are giving. These are videos are in fact, this channel in fact is dedicated free platform available for the benefit of students, or those who are interested in understanding and learning machine, ML, machine learning, artificial intelligence. And we'll be having, in fact, various, development of various series, and those series will be for different purpose. This is for machine learning fundamentals, and then there will be other series which will be in the related area, maybe machine learning for fraud detection. There can be one more area of AI. There will be separate series for in fact security, or use of machine learning for security, cyber security, different kinds of in fact aspects. Those will be discussed. Thank you once again for joining. Please provide us your valuable feedback, and see you on the other side with one more, in fact, type of we're going to discuss probably the Gaussian mixture model, GMM. So that is something which we are going to discuss, and see you on the other side with one more very interesting machine learning, unsupervised machine learning model. Thank you once again for joining.